Так, она должна, наверное, красненьким загореться, она что-то не загорелась. Это нормально? Загорелась, она просто не сразу, да. Так, ну что там, видно что-нибудь? Видно? И слышно? Слышно, да? Ага. Можно начинать, значит. Хорошо. Okay, so today our first goal will be to extend Gelfand's theory of commutative Banach algebras to the non-unital case. So more specifically, we are going to define the maximal spectrum. The maximal spectrum and the Gelfand transform. For non-unital Banach algebras. Non-unital algebras. So we start with a commutative algebra, A. At this point, we don't assume that it's a normed algebra or a Banach algebra. So just an algebra, a commutative algebra, but not necessarily unital. It turns out that in the non-unital case, the set of all maximal ideals is no longer relevant. It is much more convenient to consider only those maximal ideals which have the following extra property. We say that an ideal I of A is modular. Some people also say regular in this case. If the quotient of A modulo I is unital. Well, explicitly, if we write this down explicitly in terms of the algebra A itself, this property means that there is an element U in A whose coset modulo I is an identity here. So explicitly, this means that for every A in A minus AU belongs to I. And every such element U is called a modular identity. A modular identity for I. So clearly, if it exists, then it is unique modulo I. So the difference of any two modular identities is an element of I. Well, let's make some simple observations related to this notion. First of all, it's clear that A is unital if and only if the zero ideal is modular, just by the very definition. And actually, this means precisely that all ideals of A are modular. Well, it's clear that a quotient of a unital algebra modulo any ideal is a unital algebra. Second, let's observe that if you have two ideals, I and J, and I is contained in J, and if I is modular, then so is J. So any bigger ideal than I is also modular. It's clear, for example, from this property, it's clear that any modular ideal for I will be automatically a modular ideal for any bigger ideal, a modular identity for any bigger ideal. So J is also modular with the same modular identity. Property 3, observation 3, is that if we have a character chi of A, that is an algebra homomorphism to the complex numbers, then its kernel is a modular ideal. It's clear because if chi is non-trivial, then the quotient of A modulo the kernel is isomorphic to the complex numbers, which is obviously unital. If chi is trivial, then the quotient of A modulo the kernel is 0, which is also unital. Let's now look at a simple example of a non-modular ideal. In fact, this is not just an example, but this example actually describes a rather general situation. Let's denote by A squared the linear span of all products AB, where A and B run over our algebra. And let's observe that if A squared is strictly smaller than A, then every vector subspace I, which sits somewhere in between A squared and A, every proper vector subspace which satisfies this condition, is a non-modular ideal. Well, indeed, these inclusions imply that the quotient of A modulo I is a non-zero algebra with trivial multiplication, with multiplication which is identically 0. So this algebra is not unital. Here is a concrete example. For example, we can take the principal ideal in the polynomial algebra generated by the variable t. So this is our non-unital algebra. And I will be just A squared. So it consists of all polynomials starting with t squared. This is a non-modular ideal, because this is a special case of this general situation. Okay. One of the main advantages of modular ideals is the following simple result, proposition. Each modular ideal, each proper modular ideal of A is contained in a maximal modular ideal. It's contained in a maximal modular ideal. The proof is a simple exercise for you. So just look at the proof of the respective result for unital algebras. So at lecture 2, we proved that each proper ideal of a unital algebra is contained in a maximal ideal. And modify this unital proof to the case of modular ideals in a non-unital algebra. The proof is more or less the same, just a little modification is needed. And a warning, for non-modular ideals, this fails. The result fails for non-modular ideals. In other words, a proper ideal of a non-unital algebra is not necessarily contained in a maximal ideal. Concrete counterexamples are contained in our first exercise sheet, which is already available at the web page of the course. So probably this is one of the main advantages of modular ideals. Every proper modular ideal is contained in a maximal modular ideal. Okay. So now we define the maximal spectrum. The maximal spectrum of A to be the collection of all maximal modular ideals. Maximal modular ideals of A. And just like in the unital case, we define the character space. The character space of A is the set of all non-zero characters. And we denote it by A hat. Set of all non-zero characters. Well, since the kernel of a character is a modular ideal, it's clear that we have a map, again, just like in the unital case. We have a map from the character space to the maximal spectrum, which takes every character to its kernel. This is a maximal modular ideal. And again, just like in the unital case, this map is easily seen to be injective. This is, again, a little exercise for you. This map is always injective. The proof is a little modification of the proof for unital algebras. Let's now recall that for commutative unital Banach algebras, this map was bijective. So what happens for non-unital commutative Banach algebras? Well, it's natural to expect that this map will also be injective, will also be bijective for arbitrary commutative Banach algebras. And to prove this result, it is convenient to enlarge these two sets a little bit. So let's introduce some notation. We denote by A hat plus the set of all characters of A, including the zero characters. So in other words, this is the union of A hat and the zero character. And similarly, we enlarge the maximal spectrum. We denote by max plus of A, the union of the maximal spectrum and the algebra A itself. The algebra A itself is, of course, an ideal in itself, but it is not a proper ideal, and so it is not a maximal ideal. So we add it to our set and get a bigger set. So each of them is obtained by adding a single point to A hat and to the maximal spectrum, respectively. We have the following proposition. Consider the following diagram. We start with the maximal spectrum of the unitization of A, and consider the map from this spectrum, from the maximal spectrum of the unitization to max plus of A. And this map takes every maximal ideal of A plus to its intersection with A. We can also consider the character space of the unitization of A plus hat, and consider a map from here to A hat plus, which takes every character chi of the unitization to its restriction to A. And finally, we have two vertical arrows here. And each of them takes every character of the respective algebra to its kernel. So what we want to show, I claim that, first of all, this diagram is well defined. So what is actually well defined? I mean that if I is a maximal ideal of A plus, then this intersection is a maximal modular ideal of A, or it can be equal to A itself. So this arrow indeed takes this set to this set. So the diagram is well defined. And the horizontal arrows are bijections. The proof is a nice algebraic exercise for you. So let's observe that the bijectivity of this arrow, of the bottom horizontal arrow, is just a special case of the universal property of unitizations. So there's a one-to-one correspondence between characters of A and unital characters of A plus. So this is just a special case of universal property of unitizations. The bijectivity of this arrow is not so obvious, so let me give you a little hint of how to prove that this arrow is bijective. Probably the most tricky point is to prove that this arrow is surjective. And here's a hint of how to prove that this arrow is surjective. Let's start with a maximal idea, an ideal of A. Suppose J is a modular ideal of A. Is a modular ideal, and U is a modular identity. The modular identity for J. We define an ideal in A plus as follows. We let I denote the direct sum of J and the one-dimensional space spanned by 1 plus minus U. And I claim that I is actually an ideal. I is an ideal of the unitization of A plus. And the quotient of A plus modulo I is isomorphic to the quotient of A modulo J. This is a simple verification. And this procedure easily implies that this arrow is surjective. Because if J was not just modular but maximal modular ideal, then this is a field. So this one is also a field, and this implies that I is a maximal ideal of A plus. So this trick shows that this arrow is surjective. And the remaining parts of the proof are exercises for you. Okay, so this is true for any commutative algebra A. Now let's look what happens if A is a commutative Banach algebra. So from now on, we assume that A is a commutative Banach algebra. Then we have the following corollary of this proposition. First of all, I claim that all maximal modular ideals of A are closed. All maximal modular ideals of A are closed in A. And second, all arrows in this diagram, well, let's denote it by D. All arrows in the diagram D are bijections. And as a corollary, part 3, the canonical map from A hat to the maximal spectrum of A, which takes every character to its kernel, is a bijection, just like in the unital case. Well, indeed, why is it so? Let's look at the diagram. We already know that all maximal ideals of A plus are closed in A plus, because A plus is unital. And so since this arrow is bijective, and so all maximal ideals of A plus are of this form, and clearly, of A, all maximal modular ideals of A are of this form, and clearly they are closed in A, because I is closed in A plus. Why all arrows are bijections? Well, we already know that the horizontal arrows are bijections for any commutative algebra. But since A plus is a Banach algebra, we know that this arrow is a bijection. And now by the commutativity of the diagram, the remaining arrow, this one is also a bijection. And if we restrict this arrow to A hat itself, we get that this map is a bijection. Okay, let's now topologize the maximal spectrum. This is done exactly as in the unital case. Definition, the Gelfand topology on the maximal spectrum of A, which is identified with A hat by means of this bijection, and also on the set max plus of A, which is identified with A hat plus by means of diagram D, is by definition the topology induced from the dual space A star equipped with the weak star topology. So both A hat and A hat plus are contained in A star because all characters are continuous. And we simply induce the weak star topology on these sets. So what can we say about the resulting topological spaces? We have the following proposition. First of all, I claim that the maximal spectrum of A and the bigger set max plus of A, they are Hausdorff, which is clear because A star with the weak star topology is Hausdorff. Max plus of A is compact. And moreover, it is homeomorphic to the maximal spectrum of the unitization of A. As for the maximal spectrum itself, we can only claim that it is locally compact. Max of A is locally compact. And max plus of A is nothing but the one-point compactification of the maximal spectrum. max plus of A is the one-point compactification of max of A. Actually, there is nothing to prove here, because all these results follow from what we know about commutative unital Banach algebras and from diagram D. Well, indeed, we know that all arrows are bijections. We know that this set is compact, this space is compact. So this restriction map is obviously continuous. So this one is also continuous. Well, a continuous bijection of a compact space onto a Hausdorff space is a homeomorphism. So these two spaces are compact and homeomorphic by means of the upper horizontal arrow of the diagram G. And the last two statements about the maximal spectrum follow from the fact that if we remove a point from a compact Hausdorff space, we get a locally compact Hausdorff space whose one-point compactification is homeomorphic to the original compact space. And that's it. Okay, let's now define the Gelfand transform. Again, the definition is exactly the same as in the unital case. We define the Gelfand transform of an element little a in our algebra A to be the function a hat on the maximal spectrum, given by the following formula. So if we identify the maximal spectrum with the character space, a hat, then a hat takes a character chi to chi of A, exactly as in the unital case. So what can we say about this function? In the unital case, we proved that this function is continuous. Here, I claim that this function is not only continuous, but it also vanishes at infinity. A hat is a continuous function vanishing at infinity. Before we prove this result, let's recall that if X is an arbitrary locally compact Hausdorff topological space, then the algebra C0 of X of continuous and vanishing at infinity functions consists exactly of the restrictions to X of those continuous functions on the one-point compactification which vanish at infinity. So in other words, a continuous function vanishes at infinity if and only if it vanishes at infinity literally. So now we can easily prove our proposition. The easiest way of doing this is to extend a hat to the bigger set max plus of A. So we extend a hat to a function on max plus of A, which is identified with A hat plus. So let's recall that this is the set of all characters on A, including the zero character. And the topology on this space is induced from the weak star topology on A star. How do we extend a hat to this bigger space? Well, we extend it by using exactly the same formula. A hat is now defined on A hat plus, and it takes every character chi to chi of A. Now the same argument as in the unital case shows that A hat is continuous. A hat is continuous on A hat plus. This follows from the same argument as in the, as in the unital case. And what if we evaluate A hat at 0, at the 0 character? Well, so what do we see? We see that A hat is a continuous function on the one-point compactification of A hat, and this function vanishes at infinity. Now, by using this equality, we conclude that A hat sits in C0 on the character space. And that's it. So now if we do this procedure for all elements of our algebra, then we get a map from A, from our algebra A, to the algebra of continuous and vanishing at infinity functions on the maximal spectrum. Now this map is called the Gelfand transform of our algebra. The Gelfand transform of A is the map gamma A from A to C0 on the maximal spectrum, which takes every element little a to the function A hat. It's useful to compare the Gelfand transform of A with the Gelfand transform of its unitization. This relation is given by the following picture. So this is the Gelfand transform of A. Gamma A. This algebra C0 on the maximal spectrum is identified with an ideal in the algebra of continuous functions on max plus of A. Because max plus of A is the one-point compactification of max of A. And this one consists of those functions on the compactification which vanish at infinity. Okay, now we know that the set max plus of A is homomorphic to the maximal spectrum of the unitization. So this algebra is isometrically isomorphic to the algebra of continuous functions on the maximal spectrum of A plus. And let's now look at A plus. A is obviously contained in A plus, and here we have the Gelfand transform for A plus. And it really follows from our constructions that the diagram is commutative. And since we already know the basic properties of the Gelfand transform for unital algebras, we can easily deduce from this diagram the respective properties of this map. So let's summarize these properties in the following theorem. First, I claim that gamma is an algebra homomorphism, which is also immediate from the definition. Second, the norm of gamma is less than or equal to 1. This is true because this is true for this gamma. So this one is just the restriction of this one. And so its norm is less than or equal to 1. Property 3 is that for every element A of our algebra, the supremum norm of the Gelfand transform is equal to the spectral radius of A. Again, this equality follows from the respective equality for gamma A plus. And the spectrum for every element little a in our algebra A, the spectrum of this element, or more exactly the non-unital spectrum, because we don't assume that A is unital, and only the non-unital spectrum sigma prime is defined. So this is equal to the range of Isgolfan transform, but not exactly. We must also add 0 here, because 0 always sits in the non-unital spectrum. And indeed, why is it so? The non-unital spectrum of A is the spectrum of A in its unitization, and it's equal to the range of the Gelfand transform on this set. But the range of the Gelfand transform little a hat on this set is nothing but this one together with 0. So a hat vanishes at 0. And finally, property 5, the kernel of the Gelfand transform is equal to the intersection of all maximal modular ideals of A. And this intersection is equal to the set of all quasi-nilpotents. Quasi-nilpotent elements of A. Again, this also follows from the respective property of the Gelfand transform of the unitization. So the proof follows from the properties of gamma A plus and from the diagram. Okay, so now we know everything about commutative Banach algebras. Well, maybe not everything, but all basic results. We know all basic results about commutative Banach algebras. And so we are ready to introduce C-star algebras. So suppose that A is an algebra, at this point just an algebra without any norm. We give the following definition. An involution on A is a map from A to itself, which takes every element little a to another element little a star of the same algebra, such that the following axioms are satisfied. First of all, this map is an involution in the usual set theoretic sense. That is, if we apply it twice, then we get the identity map. That is, A double star is equal to A. Second, this map is antilinear over the complex numbers. That is, if we consider a linear combination, lambda A plus mu B, then the result will be lambda bar A star plus mu bar B star, where lambda bar and mu bar are complex conjugates to lambda and mu. For all complex numbers lambda and mu, and for all elements A and B in our algebra. And finally, property 3 is that our involution is a ring anti-homomorphism, in the sense that A B star is equal to B star A star for all A and B. An algebra equipped with an involution is called a star algebra. A star algebra. We now define a Banach star algebra. So by definition, a Banach star algebra is a Banach algebra A equipped with an involution such that the involution is isometric, such that the norm of A star equals the norm of A for all elements in A. And finally, let's now give our main definition. A C-star algebra. A C-star algebra is a Banach star algebra A, such that the following extra axiom is satisfied. The norm of A star A equals the norm of A squared for all A. And this identity is sometimes called the C-star axiom or the C-star identity. And by the way, I forgot to say that the element A star is usually called the adjoint of A. Let me write it down here. A star is called the adjoint of A. Сейчас доберемся до этого. Там будет для C-звездочки это не просто вложение, но сейчас мы до этого доберемся скоро. The announcement is that the Gelfand transform of a commutative C-star algebra is actually an isomorphism onto C0x, onto C0 on the maximal spectrum. This is one of the fundamental results which will be probably proved at the beginning of the next lecture. Or maybe at the end of today's lecture, I don't know exactly. Okay, so these are our main objects. Let's now introduce morphisms between them. So a natural class of morphisms between star algebras consists of those algebra homomorphisms which preserve the involution. They are called star homomorphisms. If we have two star algebras A and B, and an algebra homomorphism phi from A to B, then we say that phi is a star homomorphism. Star homomorphism if it preserves the involution. And one more general definition. If A is a star algebra, and if B is a subalgebra of A, then we say that B is a star subalgebra. B is a star subalgebra if it is stable under the involution. If for every element little b in our algebra, the adjoint of B also belongs to the subalgebra. So it's clear from the definition that a star subalgebra of A is also a star algebra for the same involution. Also, a closed star subalgebra of a Banach star algebra is also a Banach star algebra. And the closed star subalgebra of a C star algebra is a C star algebra. Well, maybe let me write this down explicitly. Remark: a closed star subalgebra of a C star algebra is a C star algebra. Okay, let's now look at some basic examples of C star algebras. Example 1. Well, of course, the zero algebra is a sister algebra for trivial reasons. And also the complex numbers form a sister algebra. So they are sister algebras. The involution on the complex numbers is just the complex conjugation. Example 2. Let's now look at the algebra of bounded functions on an arbitrary set. If X is any set, then the algebra little L infinity of X of all bounded complex valued functions on X is actually sister algebra. We already know that this is a Banach algebra for the pointwise product, pointwise multiplication. And the involution is just the pointwise complex conjugation. Again, it's immediate that all sister algebra axioms are satisfied. So it is a sister algebra. Example 3. Example 3. If now X is a topological space, then we can consider the algebra CB of X of all continuous bounded functions, of all continuous bounded functions on X. This is easily seen to be a closed star subalgebra of L infinity of X. And also we can look at C0 of X, which consists of all continuous and vanishing at infinity functions on X. And this is a closed star subalgebra in here. So this is a chain of closed star subalgebras. So all of them are sister algebras. So let me stress once again that among these examples, this is C0 of X is probably the most important one because one of the fundamental results, the so-called the first Gelfand-Naimark theorem, states that every commutative sister algebra is isometrically isomorphic to C0 of X, or more exactly, to the algebra of C0 on the maximal spectrum. Another useful example is the algebra Beagle infinity on a measure space. Example 4. Example 4. Beagle infinity of X mu, where X mu is an arbitrary measure space, is also a sister algebra. We know that this is a Banach algebra, and to make it into a sister algebra, we again define the involution to be the pointwise complex conjugation. And again, just like in example 2, all axioms are satisfied. So this is a sister algebra. Well, okay, so far all these examples are commutative. The basic non-commutative example of a non-commutative sister algebra, example 5, which actually serves as the main motivation to introduce sister algebras, is the algebra of bounded linear operators on a Hilbert space. If H is a Hilbert space, then B of H, the algebra of bounded linear operators on H, is a sister algebra. Well, indeed, we know that this is a Banach algebra. The algebra of bounded linear operators on any Banach space is a Banach algebra. And let's also recall the standard construction from functional analysis that for any operator, for any bounded linear operator on the Hilbert space, we can define its adjoint. For for every t in B of h, the adjoint operator T star is uniquely determined by the following formula. The inner product of T star x and y is equal to the inner product of x and t y for all x and y in H. So this is one of the possible definitions of the adjoint operator. Another canonical definition defines T star in terms of the dual operator on the dual space, and which is set theoretically identified with H itself by the Riesz representation theorem. But this is maybe the most compact definition of the adjoint operator, which doesn't involve dual spaces. Well, it's a standard fact of functional analysis that this C star identity, this formula, holds in B of H. So B of H is a C star algebra. There is a special name for star homomorphisms with values in B of H. So let's introduce the respective terminology. If A is any star algebra and H is a Hilbert space, then a star representation of A on H is a star homomorphism pi from A to B of H. So star homomorphisms with values in B of H are called star representations. And if the kernel of pi is trivial, then we say that pi is faithful. Pi is faithful if the kernel of pi is trivial. In Russian, we usually call such representations точные представления. This is not an exact translation, but this is more or less standard terminology. The algebra B of H, this example 5, is important not only because it serves as the main motivation to introduce C star algebras, but also because it is, in some sense, this example is universal. We will see shortly that every C star algebra can be isometrically embedded into B of H for a suitable Hilbert space H. And this is the so-called the second Gelfand-Naimark theorem. Какая? Здесь-то? В определении нет, не обязательно. This definition makes sense for all star algebras, not necessarily Banach star algebras. We will use it mostly for Banach star algebras and for C star algebras, but formally it makes sense for any star algebra. Okay, let's now look at some non-examples. That is, at some examples of Banach star algebras which are not C star algebras. Example 6. An example and exercise at the same time. Let's look at the algebra of n times continuously differentiable functions on a closed interval AB. Then this is a Banach star algebra. We know that this is a Banach algebra, and we can easily define an involution by the same old formula. The involution is just the pointwise complex conjugation. But this algebra is not a C star algebra if n is greater than or equal to 1. It is not a C star algebra unless n equals 0. Another example is the disk algebra. This is example 7. Example exercise 7. The disk algebra. Which is denoted by A of G. This algebra was discussed at the first lecture. And let's recall that this algebra consists of those continuous functions on the closed unit disk, which are holomorphic on the open disk. So here D is the open unit disk on the complex plane. So we know that A of D is a closed subalgebra in C of D in the algebra of continuous functions, so it is a Banach algebra. And this algebra is a Banach star algebra. A of D is a Banach star algebra with respect to the following involution. Well, we cannot define the involution of this algebra by means of this formula, because the complex conjugate of a holomorphic function is no longer holomorphic. But we can define an involution as follows. So first we apply the complex conjugation to Z, then we apply F, and then again, once again, we take the complex conjugation. And it's rather easy to see that this is indeed a Banach star algebra. But it is not a C-star algebra. It's not a C-star algebra. Another important example, which was also discussed at the first lecture, is the group algebra of the group Banach algebra of a discrete group. Example 8, example exercise 8. Let G be a group. So we don't equip G with any topology, or alternatively, we can look at G as a discrete topological group. We know that L1 of G, little L1 of G, is a Banach algebra for the convolution product, for the convolution multiplication. And we can also make it into a Banach star algebra. Banach star algebra. With respect to the following involution, F star of X is the complex conjugate of F of X inverse. So it is a Banach star algebra with respect to this involution, but again, it is not a C-star algebra. But it's not a C-star algebra, except for the trivial case where the group G is trivial. Unless G consists of a single point. That is the identity. On the other hand, there is a simple way of constructing the C-star algebra associated, canonically associated to L1 of G. And the construction looks as follows. This is our example number 9. Example exercise 9. The resulting algebra will be called the reduced group C-star algebra. So again, we start with the group G. G is a group. And we consider the space a little of G, which consists of all square integrable, more exactly, square summable functions on G. Of all functions G on F on G, such that the following series converges. And this is well known to be Hilbert space. L2 of G is a Hilbert space with respect to the following inner product. The inner product of F and G is the following sum. Over all elements in our group. Let's now consider the following representation of L1 of G on the space. Из кого? Из седьмого нельзя, но это задачка. Что там можно как-то... Нет, ее можно вложить в большую алгебру. We can always embed the disk algebra into the algebra of continuous functions on the disk. The algebra of all continuous functions on the disk is a C-star algebra. And now we are going to describe a certain canonical way of including L1 of G into a C-star algebra. So A of G can also be embedded into a C-star algebra, but this is more or less trivial. Just A of C is by construction, it is a subalgebra. A of G is a subalgebra in C of D, and this is a C-star algebra. Okay, so let's now consider the following representation of L1 of G. To define this representation, so I said that this will be an example and an exercise at the same time. So the exercise is as follows. Prove that if we take any two functions f and g, f in L1 of g and g in L2 of g, then their convolution is defined everywhere on G. Is defined everywhere on G. So at the first lecture we discussed the convolution of two functions from L1. But now one of them sits in L1 and another one sits in L2. But the formula which defines the convolution is exactly the same. So it turns out that this function is also defined everywhere on G and actually belongs to L2 of G. And the L2 norm of this function is less than or equal to the L1 norm of f, to the product of the L1 norm of f and the L2 norm of G. So we can always convolve L1 functions and L2 functions. And second, we can now consider the following map, lambda, which acts from L1 of G to the algebra of bounded operators on L2 of G. And this map takes every function f to the convolution operator, lambda of f, which takes g to the convolution of f and g. And I claim, or more exactly, I recommend you to prove that this map is a faithful star representation. Is a faithful star representation of L1 of G. Okay, so it is a faithful star representation, and this originally implies that its image is a star subalgebra in the algebra of bounded linear operators. So the closure of this image is a C-star algebra, and it is called the reduced group C-star algebra. The reduced group C-star algebra of G is defined, it is denoted like this, C star R of G. It's defined to be the closure of the image of lambda. So it is a closed star subalgebra, so it is indeed a C star algebra. So as a result, we see that we have a star homomorphism lambda from L1 of G, from L1 of G to the reduced group C star algebra, C star R of G, which has dense range by construction. It turns out, by the way, that if G is abelian, then L1 of G is also commutative, and this map lambda can be identified with the Gelfand transform of L1 of G, which in turn can be identified with the Fourier transform. And this is, again, one of the exercises in the exercise sheet 1. Well, a natural question is why this algebra is called the reduced. Why is it reduced C-star algebra of G? In fact, there is another C-star algebra canonically associated to G. It is called the full C-star algebra, and it is defined in terms of a suitable universal property. And in the general case, the reduced star algebra is a quotient of the full C-star algebra, so they are not the same. But in the important special case where the group G is amenable, these two C-star algebras are the same. But this is a totally different story, so we will not discuss amenability in our course, in spite of the fact that this is a very important property. Okay. So these are the basic examples of C-star algebras. Now let's look at two important constructions. Namely, let's talk about products and unitizations of C-star algebras. It's rather easy to define the product of two C-star algebras. Let's observe that if we have two star algebras A and B, star algebras, then their product, which is also commonly denoted as direct sum, is also a star algebra. Is a star algebra. The involution on the direct sum is defined in an obvious way, like this. Also, it's rather easy to observe that if they are Banach star algebras, if A and B are Banach star algebras, then so is their direct sum. More exactly, the norm on the direct sum is the maximum of the norm of A and the norm of B. And this is easily seen to a Banach star algebra. And finally, the third observation, if they are C-star algebras, if A and B are C-star algebras, then this norm on their direct sum is easily seen to satisfy the C-star axiom. So the direct sum is also a C-star algebra with respect to this norm. Okay, let's now talk about unitizations of C-star algebras. This construction is a little bit less obvious. Again, we start with a simple observation. If we start with a star algebra, that is just an algebra equipped with an involution, then there is a canonical involution on the unitization. If A is a star algebra, then its unitization is also a star algebra. The involution on the unitization is given by the following obvious formula. And moreover, if A is a Banach star algebra, then the unitization is also a Banach star algebra. So this is the formula which defines an involution on A plus. And the norm on A plus was discussed at the previous lecture. The norm of this element is defined to be the norm of A plus the absolute value of lambda. Now a natural question is, what if A is a C-star algebra? And here we have a little problem because of the following exercise. If A is a C-star algebra, then this norm doesn't satisfy the C-star axiom. Let's denote this formula as 1. So this norm doesn't satisfy the C-star axiom, except for the trivial case where A is 0. Okay, so what to do? It would be nice to have the construction of unitization for C-star algebras, but this norm doesn't work. Fortunately, there is another way of defining a norm on the unitization of C-star algebra, such that this norm does satisfy the C-star axiom. And for technical reasons, to define this norm, we have to consider two cases separately: the case where A is not unital and the case where it is unital. So let's start with the more interesting non-unital case. We have the following proposition. Suppose that A is a non-unital C-star algebra. And here by non-unital, I mean strictly non-unital. So we assume that it doesn't have an identity. For every element A in its unitization, we define the left multiplication operator, LA, on A, which acts by the following formula. So it is well defined because A is an ideal in A+. And we define the norm of A. So in order to distinguish between the norm on A and the norm on the unitization, I'll put the plus sign here. So we define the norm of A to be the norm of this multiplication operator LA. So explicitly, this is the following supremum. The supremum of the norms of all elements A, B, where B runs over the closed unit ball of A. I claim that what we get is indeed a norm. This function is a norm on the unitization on A+. Second, this norm extends the original norm on A. And finally, if we equip A+ with this new norm, then this is a C-star algebra. So we see that this proposition gives us a way of defining a C-star norm on the unitization. The proof depends on two lemmas. Lemma 1 is a simple lemma from classical functional analysis. You will have a norm space E, a norm space, and the codimension 1 subspace E0, a vector subspace of codimension 1. Then if E0 is a Banach space, then E is also a Banach space. If E0 is a Banach space, then so is E. And this is an exercise for you, lemma exercise in classical functional analysis. And lemma exercise 2 which actually simplifies our original definition of a C-star algebra. If A is a Banach star algebra, sorry, not a Banach star algebra. If A is a Banach algebra equipped with an involution, such that the following inequality holds. For all elements in our algebra. Then A is actually a C-star algebra. Then A is a C-star algebra. In other words, this inequality automatically implies that the involution is isometric, and it automatically implies that this inequality is actually an equality. This is a short and nice exercise for you. Okay, now we can prove our proposition. Oh, sorry, I see it's time to finish. Okay, well, let's do it at the beginning of the next lecture. And we will also need to discuss what to do if f is already unital. Because as we will see, the proof of this proposition fails if A is already unital. So if A is already unital, then we have to invent another way of defining a norm on the unitization. So at the next lecture, we discuss this proposition, and then we prove some basic spectral properties of C-star algebras and induce from them the first Gelfand-Dirac theorem, which states that the Gelfand transform of a commutative C-star algebra is actually an isometric star isomorphism. This will follow from the proof. When we prove this result, when we will prove this result, we will see that to prove that this is indeed a norm, we will need the assumption that A is not unital. If A is unital, then this is a semi-norm, but it is not a norm, which is more or less clear from the construction. If we look at if A is unital, and if we look at this element,